Welcome back. We're going to talk about 10.8, the power theorems today. We're going to start off with a theorem, the chord power theorem. We're going to look at this figure over here on the right. If two chords intersect at the interior of a circle, so here we have two chords, they both intersect at this point. The product of the segments of one chord is equal to the product of the segments of the other chord. So in this figure over here, what that means is this length A multiplied by the rest of the chord, that length B, is equal to this length C multiplied by the rest of the length of the chord D. So that is the chord power theorem. Let me provide you some quick little proof for this. This is not going to be an official proof or anything. But if I create two triangles here, I want you to notice that this angle right here where my cursor is shares endpoints with this angle where my cursor is now. So these two inscribed angles, they are congruent to each other because they share an intercepted arc. The intercepted arc divided by 2 is the inscribed angle. Same thing over here, this inscribed angle where my cursor is, and this inscribed angle where my cursor is, they also share an intercepted arc, so they are going to be congruent. And of course, we have vertical angles here at the center. So what we have is two triangles that are similar to each other by the angle-angle similarity postulate. And if we were to set up our similarity statement and then come up with a proportion, cross multiply and solve, you would find that this relationship is true. So similar triangles brings us this relationship. On to example one. I think you can do this one on your own. Pause the video now and try out number one. All right, we're going to apply the chord power theorem here. We have two chords that are intersecting in the center, or in the, not the center, but on the interior of a circle. So 18, that is part of one of the chords, multiplied the rest of the chord's length, which is 2. 18 times 2 is equal to this other chord here is 10 and x, so one segment is 10, multiplied by the rest of the length of that segment, that chord, which is x, so 10 times x. We solve and we get x equals 3.6. 3.6. On to the secant power theorem. So if two secants come from the same exterior point, here you see point C. So we have two secant lines coming from that same exterior point. Then the product of the whole length of one secant and its outside segment. I'm going to highlight a couple things here. So let me pause the video. Okay, so the key here is the whole length and the outside segment. So if two secants come from the same exterior point, that would be point C, then the product of the whole length, what would the whole length be? It would be AC. And the outside segment, what is the outside segment? BC, is equal to the product of the other secant's whole length, that would be EC. So let me highlight here, whole length, and its outside segment. Okay, so what does that look like for this? Right down here, the whole length of secant AC is going to be AC, multiplied by the outside segment, which is BC. So you see that AC times BC is equal to the whole length of the entire other secant, EC here, multiplied by the outside segment, DC. All right, so this also works because of similar triangles. It's a little more complicated as compared to the one above. There is a good proof of this in your book if you want to take a look at that. On to example 2. So use the secant power theorem and work number 2 now. Find the value of x. Pause the video now. Work example 2. Okay, so the length of the whole secant is 8 plus 10, 18. The outside segment is 10, so 18 times 10 gives us 180. The other secant has a length of x plus 6, so x plus 6, multiplied by the outside segment, which is 6. Now, make sure that x plus 6 is in parentheses. We do have to distribute 6 into the parentheses. That's going to give us 6x plus 6 times 6 is 36. We solve for x, and we get x equals 24. There you go. On now to the secant tangent power theorem. Very similar to the secant power theorem. If a secant and tangent come from the same exterior point, then the product of the whole length of one secant and its outside segment is equal to the product of the tangent multiplied by itself. So one more time. If the secant, or if a secant and tangent come from the same point on the exterior, that is point C here, then the product of the whole length of one secant, what is the whole length? It is AC. That is the length of the whole secant. If you're going to mess this up, that's probably where you messed it up. You're probably, instead of saying AC, you might say AB. So if you made an error on number 2, I bet that's where you did it. So the whole thing is AC multiplied by its outside segment, which is BC, is equal to, and you'll see that here, AC times BC, is equal to the product of the tangent multiplied by itself. So that'd be CD squared. That is the secant tangent power theorem. So go ahead and use that secant tangent power theorem now to work example 3. Pause the video now, work example 3. Okay, so the whole secant, 9 plus 16 is 25, multiplied by the outside segment, which is 16, so 25 times 16, is equal to the tangent multiplied by itself, that is x times x, or x squared. So we get x squared equals 25 times 16 is 400. Take the square root of both sides. Now remember, when we're solving for a variable and we take the square root, we do need to say plus or minus. On this particular problem, x cannot be negative 20. When we take the square root of 400, we do get 20. So just keep in mind that length must be positive, but sometimes we do have the situation where we do need to take the square root of a variable, and this plus or minus does need to be used, even though we are, that is an extraneous solution here. Very good. Thanks for sticking with me. Good luck on the assignment.